This conference will now be recorded.
Good morning, all. Today is the second class of, actually third class. First class we discuss only syllabus, regarding syllabus and reference textbooks, and one example of electronic system. In last class we discuss, okay, yes, in last class we discussed few basics of semiconductor materials and few properties of semiconductor materials and charge carriers in solids, and what is the definition of covalent bonds, how covalent bond is formed, right? And a part of a periodic table, right? Don't remember entire periodic table, only remember these three, third group, fourth group, and fifth group only, right? Here mainly we are mainly concentrated on silicon and germanium also, right? Compared to silicon and germanium, we use only silicon only, right? Okay, anyhow, concentrate on silicon and germanium. And also third group elements, boron, aluminum, gallium, and fifth group elements, phosphorus and arsenic. Why these elements are classified third group, fourth group means, in outermost cell, that is valence electrons, number of valence electron in aluminum or gallium or boron is 3, whereas number of electrons in outermost cell silicon and germanium and carbon is 4. And coming to the phosphorus and arsenic, and number of electrons in outermost cell is 5. So that based on the number of cells in the outermost cell, the elements are classified in periodic table, right? And why? Because already we know, right? The main, observe this line, the atom's chemical activity is determined by the electrons in the outermost cell, is called the valence electrons. And how to complete this cell is, right? So that's why mainly concentrate on valency electrons, right? And also we discuss how covalent bond is formed, right? What is meant by a crystal, silicon crystal, right? This type of arrangement is called a silicon crystal, right? In that all free electrons are attached with another atom free electrons, so that they form a covalent bond. And what is the definition of holes, right? At room temperature only few, right? At 0 degree Kelvin it acts as a insulator, there is no conduction, but as temperature increases there may be chance few electrons break up the covalent bond and they act as a free electron. Okay, until that is a valence electron available in covalent bond. Once the electron acquires sufficient energy and break the covalent bond, now it becomes a free electron. It is a free charge carrier. And one more thing is, once if electron breaks the electron means in that place there is a one place is created, one empty place is created, that act as a hole, right? In particularly, especially in semiconductors, hole is also a free charge carrier, right? In semiconductor, the current conduction taking place due to electron as well as holes. So we mainly concentrate on electrons as well as holes. Why? Because the current conduction taking place holes as well as electrons. And what is the direction of hole direction and electron direction? These are the opposite direction. In this figure, suppose this is a hole. Observe the hole direction, that is from left to right. Okay, electron also moving from right to left, opposite direction. And also we discuss what is band gap energy, right? Uh, what is the minimum energy required to dislodge an electron from covalent bond? How the electrons break the covalent bands? What is the minimum energy required? That energy is called the band gap energy. For a silicon material, that band gap energy is equal to 1.12 into electron volt, right? And what is meant by electron volt? Electron volt is nothing but a moving a one electron, the difference of 1 volt difference, and that value also given, right? That is equal to 1.6 into 10 power minus 19 joules. And there is a one formula, number of charge carriers mainly depends upon the EZ and temperature. Okay, remaining all are constant values. EZ is the band gap energy and T is the temperature. Okay, already we discussed all these things. And one important point here is at room temperature, the number of available charge carriers is 1.08 into 10 power 10 electrons per cubic centimeter. Similarly, volts also same. What is the volts? Volts also same, 1.08 into 10 power 10 volts per cubic centimeter. At T is equal to 600 Kelvin. Okay, these are the electrons as well as volts. And also I given some problem. Calculate the number of charge carriers. T is equal to 900 Kelvin as well as T is equal to 1200 Kelvin. Only in the group, only 4 to 5 people answered, and personally, some people are sent to my WhatsApp number. Total around maximum 9 people are responded, right? Nearly out of 120, 130 students, only 10 students are, I think, active, right? I don't know whether remaining people are, why they are not active, right? Okay, try to slow. What we are is during this lockdown period, we try to in touch with students. Okay, we try to introduce. Then only we give them some basic concepts of electronic devices and circuits. That is the main idea, right? Don't think it is a bore class, right? And the study of semiconductors also very important, basic, right? So far we are not enter into diodes. Okay, that is another issue. Okay, if I give some problem, try to respond, right? To solve a simple problem, the response is very poor response. Okay. Now coming to the, it is here important observation is at room temperature, number of electrons, this much electrons, but available atoms per cubic centimeter. What is available atom per cubic centimeter? 5 into 10 power 22. Available atoms are huge number of atoms, 5 into 10 power 22. So that means what it identified, we recognize that only 1 in 5 into 10 power 12 atoms benefit from a free electron at room temperature, right? So up to this level also silicon is still seems a very pure conductor, right? But do not disappear. We next introduce means of making some silicon is more easy. Up to that we discuss in last class, right? And how many students are joining here? Okay, 79 students are joined. Now again there is a one more presentation. Okay, this is PPT available from net also. Right, once again we discuss. Okay, this is some, observe this one is silicon atom. Here what is plus 4 indicates? Here the plus 4 indicates positive charge protons. Right, here the minus symbol indicates electrons. Right, always the atom is neutral. right? Plus 4, here minus 4. The total always the atom is neutral. Here minus symbol indicates the electron, 4 valency electrons, right? Okay, now you need to draw the symbol like a circle, one more circle, first cell, second cell, right? Okay, that is not necessary. Try to represent atoms like this. Simple one small circle, inside plus 4, that is a proton charge, and outermost cell electrons, 4 electrons, negative charge. These are all the valence electrons. How the covalent bond is found means this electron is combined with another atom valence electron, then form a one covalent bond. Here one covalent bond, here one covalent, here one covalent bond. Okay, like that. 4 valence electrons form a 4 covalent bonds. Here observe here 4 directions. Okay, in middle silicon atom form a 4 covalent bonds. Right, strong 4 covalent bonds. Okay, now this type of structure is called a lattice. The atoms form a lattice structure. This type of arrangement is called a lattice structure. Now, what happens? Silicon at low temperatures, all covalent bonds are intact, right? They are tightly bound. No electrons are available for conduction, and conductivity is 0. So remember this one, at low temperature or 0 degree Kelvin, so all covalent bonds are tightly bonded, no electron is available for conduction, so that conductivity is 0. Now at room temperature 300 degree Kelvin. This is silicon at low temperature means 0 degree Kelvin. Now here some covalent bonds break, freeing an electron, creating a hole due to thermal energy. Right, as temperature increases, okay, we consider some at room temperature. Already we discussed some electrons acquire sufficient energy, they will break the covalent bond. Okay, then the conductivity. Okay, conductivity here in terms of is greater than 0. Okay, not use conductivity, but the conductivity point of is greater than 0. Okay, now here observe here. This is here the plus sign indicates, observe the middle atom. Here the plus sign indicates hole, right? Suppose when temperature increases, middle silicon atom acquire some sufficient energy, right? This will break the covalent bond. Okay, broken covalent bond, dotted lines. Okay, here remaining all are solid lines. Solid lines is tightly bonded. Here dotted lines indicates broken covalent bond. What happens whenever a covalent bond is broken means, observe here plus symbol. Okay, there is a hole. This one is, what is this one? Hole. Now this electron is freely available here. Red one, observe here red color, free electrons. Here minus symbol is negative charge. Right, here free electron, one free electron, and one hole is created. Remember here, at room temperature, number of electrons is equal to number of holes. Right? Here in this diagram, only one covalent bond is broken, but in coming to the practical applications, thousands of electrons broken covalent bonds. Then what is the number of electrons and number of holes? Number of electrons is equal to number of holes. Remember this one important, right? Number of electrons is equal to number of holes. Right. Now today we discuss modification of charge densities. Sorry. Modification of carrier densities or free charge carrier densities. So far, what is the problem here? The problem is still silicon very pure conductor. It seems like a very pure conductor, right? Then how to increase the conductivity of a silicon? Okay, observe here these lines. The pure type of silicon studied thus far is an example of an intrinsic semiconductors. Right, so far we studied the semiconductor. What that semiconductor is called? Intrinsic semiconductor. Intrinsic semiconductor. That is also pure semiconductor. Here the main problem is suffering from a very high resistance. High resistance means the conductivity is pure conductivity. Now, fortunately, it is possible to modify the resistivity of a silicon by replacing some of the atoms in the crystal with atoms of another material. Okay, that is one procedure developed, right? Fortunately, it is modify the resistivity of a silicon by replacing some of the atoms in the crystal with atoms of another material. Another material means other than silicon, right? By adding in other materials other than silicon, we can change the conductivity of a silicon material. Right. In an intrinsic semiconductor, the electron density n, that is equal to n. Here suffix I represents the intrinsic. Intrinsic means pure semiconductor. In pure semiconductor, what is the condition here? Electron density is equal to the hole density, right? Now this is called the mass action law. N into P is equal to Ni square. So this is always satisfied. Whether it is an intrinsic semiconductor or whether it is extrinsic semiconductor, this one is compulsory satisfied. Number of electrons multiplied with number of volts, that is equal to Ni square. Now, then how we combine, how we can modify the resistivity of silicon by replacing some of the atoms, right? Which atoms are preferable, right? Now onwards we discuss some extrinsic semiconductors, right? I think already we studied in intermediate level. Once again we recap, right, with some equations. Now observe here the periodic table. We'll go back periodic table. Okay, this is a part of periodic table. Now observe here. Suppose if you form a n-type semiconductor, okay, we introduce a fifth group elements. We introduce some atoms in intrinsic semiconductor, so that now become that is a impure semiconductor, that is also called extrinsic semiconductor. Okay, we are adding some impurity materials. Why I am saying impure means previously it is a pure silicon, that it contains only silicon atoms only. Now to modify the conductivity of a silicon, we are introducing, suppose if you make a n-type extrinsic semiconductor, introduce phosphorus or arsenics. Why? Because how many electrons are there here? 5 valence electrons are there. 4 valence electrons are formed a covalent bond. 1 electron is free. That means what it indicates? Here more number of electrons are available if we add a phosphorus or arsenic to the silicon atom. Okay. Now coming to the third group. Suppose if you make a p-type extrinsic semiconductor. P-type means holes. Observe here. What is here? This is the third group. Outermost cell consists of only 3 electrons. 3 electrons are forming 3 covalent bonds. One is the empty space, right? Unfilled covalent bond that act as a hole. So when we combine silicon with aluminum or gallium or boron atoms, then what happens means more number of holes are created in the lattice. That means what happened here? Now this type of material act as a p-type. If the p-type is holes are the majority carriers. Right, remember that while studying the semiconductors, holes also act as a charge carrier. There is a conductivity due to holes also. Right, not only electrons, especially in semiconductors, the conductivity taking place due to holes as well as electrons. Right, based on that, we can combine silicon, right? Okay, introduce some impure atoms like a phosphorus, then that becomes like a n-type semiconductor. If you add aluminum, boron, or gallium, it becomes a p-type semiconductor. Remember this periodic table, right? Okay, observe here. Now phosphorus. Recall from figure 2.0 that phosphorus contains 5 valence electrons. What happens if some of phosphorus atoms are introduced in a silicon crystal? Okay, this is the silicon crystal. In middle we introduce, let us for example, right? We introduce a phosphorus atom. We added phosphorus atom. Now this becomes an impure semiconductor, not a pure semiconductor, impure semiconductor. Now this one also called extrinsic semiconductor, right? Okay, as illustrated in figure 2.5, each phosphorus atom shares 4 electrons with neighboring silicon atoms, leaving the 5th electron unattached. Right? There is one extra atom. Now this atom acts as a free charge carrier. This electron is free to move, serving as a charge carrier. Thus, if n phosphorus atoms are uniformly introduced in each cubic centimeter of silicon crystal, then the density of free electrons rises by the same amount. Due to this, what happens means, if we introduce suppose 10 phosphorus atoms, 10 free electrons are available, right? Other than previous n into p is equal to ni square, other than previous n, now few more electrons are available for conduction, right? This is important. Thus, if n, capital N, phosphorus atoms are uniformly introduced in each cubic centimeter of a silicon crystal, then the density of free electrons rises by the same amount, right? If previously it is a n, now n plus capital N, right? The controlled addition of an impurity such as phosphorus to an intrinsic semiconductor is called a doping. Okay, here the technical word is, instead of using impure semiconductor, etc., we can call it as a doped, right? Doped semiconductor or doping. What is meant by doping? The controlled addition of impurity, the controlled, right? That is in user hand, right? During the manufacturing of a particular device, we can easily control. I require that much of current conduction through silicon, means that much of impurity atoms are added, right? Okay, the controlled addition of an impurity such as phosphorus to an intrinsic semiconductor is called the doping. Okay, we cannot add randomly, right? That is some formulas, right? How to add impurities, right? Okay, it is a controlled manner, not a random manner. It is a controlled manner. Okay, now the phosphorus itself act as a dopant, providing many more free electrons than in the intrinsic state. The doped silicon crystal now is called the extrinsic. Now the doped silicon crystal is now called a extrinsic semiconductor. More specifically, an n-type semiconductor to emphasize the abundance of free electrons. Now, again, in extrinsic semiconductor, there are two types. One is p-type and another one is n-type. Here, due to the addition of phosphorus atoms, more number of free electrons are available for conductivity. That's why this is called the n-type semiconductor. Here small n indicates the electrons, number of electrons, right? Okay, similarly, observe here, as previously we know that n into p is equal to ni square. As remarked earlier, the electron and hole densities in intrinsic semiconductor are equal. But how about these densities of a doped material, right? In that doped material also, they observed that n into p is equal to ni square only. Even though number of free electrons increases, the product of n into p, still it is equivalent to ni square only. Right? Why? Because observe here, where n and p respectively denote the electrons and hole densities in the extrinsic semiconductor. Here this one, electrons in extrinsic semiconductor and holes in extrinsic semiconductor, and this one ni square is the intrinsic carrier concentration. The quantity Ni represents the densities in the intrinsic semiconductor. Right hand side related to the intrinsic semiconductor, whereas left hand side related to the extrinsic semiconductors. Right. Hence the I subscript I indicates the intrinsic semiconductor and therefore independent of the doping level. Now here. Okay. Okay. The above result seems quite strange. How can NP remain constant while we add more donor atoms and increase N? What happens, right? Here what we observed here, more number of electrons are available by introducing a phosphorus. Okay, that is also called donors. Phosphorus also called donor. Why? Because it will donate one free electron. Now there the answer is, okay, in the equation 2.5, that P must fall below the intrinsic level as more n-type dopants are added to the crystal. Only one possibility is n increases. What about P? P compulsory decreases. Why? Because due to recombination. Sorry. Here, some of the free electrons are recombined with available holes. So that what happens means the density of holes reduces below the intrinsic level. Figure here, P must fall below the intrinsic level as more n-type dopants are added to the crystal. This occurs because many of the new electrons donated by the dopant recombine with the holes that were created in the intrinsic material. Okay, that is the reason. Why still it is constant? This is also called mass action law, right? Whether it is a intrinsic semiconductor, whether it is an extrinsic semiconductor, the mass action law must be satisfied. What mass action law states that n into p, number of holes, number of electrons is equal to ni square, right? Here there is a one problem. Observe here. Okay, what is the problem here? A piece of crystalline silicon is doped uniformly with phosphorus atoms. The doping density is 10 power 16 atoms per cubic centimeters. So how many atoms are introduced here? 10 power 16 phosphorus atoms are introduced within a cubic centimeter area. Now determine the electron and hole densities in this material at room temperature. Right. Observe here, this is the solution. The addition of 10 power 16 phosphorus atoms introduce the same number of free electrons per cubic centimeters. So number of phosphorus atoms is equal to number of free electrons, right? So since this electron density exceeds that calculated in example 2.1 by 6 times. Okay. Now what is n is equal to extrinsic here? Extrinsic semiconductor electrons. N is equal to, that is equivalent to number of phosphorus atoms. N is equal to 10 power 16. Now what according to mass action law, N into P is equal to Ni square. Right, already we know the Ni square. Ni square at room temperature. Right, what is the problem here is determine the electron and hole densities in this material at room temperature. Right, we go back to the previous problem. Right, okay, this is the previous problem. Okay, this is related to the intrinsic semiconductor only. Why? Because here suffix Ni, I is the suffix, intrinsic semiconductor. Now there is a one formula, right? This is the formula for intrinsic semiconductor. Okay, number of free charge carriers available, right? That is equal to number of electrons is equal to number of holes here, right? Now already what is that value? 1.08 into 10 power 10 electrons per cubic centimeter. Remember this one. Ni. Why? Because Ni square. We require Ni square. N into P is equal to Ni square. Right? So now substitute here. Okay. Now substitute here. So number of holes in extrinsic semiconductor P is equal to Ni square. 1.08 into 10 power 6 whole square by N, where N is equal to 10 power 6. So now what is here? Observe here 1.17 into 10 power holes per cubic centimeter, right? So now comparison with electrons and holes. Okay, here 10 power 16 electrons are there, here only 10 power 4 holes are there. So compared to the hole, okay, here more number of electrons, free electrons are available, right? Note that the hole density has dropped below the intrinsic level by 6 times. Previously, what is the hole density here at room temperature? Okay, this one is the hole density. 1.08 into 10 power 10. 10 power 10 is the hole density at room temperature. Now here what happened due to this? Okay, remaining 10 power 6 holes are recombined with electrons, right? Remaining 10 power, approximately 10 power 6 holes are recombined with electrons. So that what happens is number of holes reduces. Number of holes reduces. Here what is here? Number of electrons is 10 power 16. Number of holes is only 10 power 14. Okay. Thus, if a voltage is applied across this piece of silicon, the resulting current consists of predominantly of electrons only. Okay. Now, if we apply some voltage, if we create some electric field or apply some voltage across this piece of extrinsic semiconductor, now what happens? There is a current force in this material, but that major current is due to electrons only. Of course, there may be a small amount of current also flows due to holes. Why? Because hole concentration is 10 power 14 is the hole density, right? And don't think that all becomes zero, never becomes zero. Remember that most of the research analysis are also proved that N into P is equal to Ni square. Mass action law must be satisfied. If volts becomes zero, what happened here? Suppose I am thinking I am introduced a very huge number of phosphorus atoms. Then this huge number of electrons are recombined with almost all holes in the silicon material. Then what happens? Holes count becomes zero. Now what about mass action law? If P is equal to 0, that means this is not satisfied. So even though we introduced whatever the quantity level, right, whatever the quantities of phosphorus atoms in pure silicon, there must be at least a few holes compulsory, right? So that mass action law satisfied. So N into P is equal to N square. Don't think that we add more number of phosphorus atoms. At one time what happens means holes becomes zero. That is never happen in semiconductors, right? right? Always that mass action law should be satisfied, right? Okay, the conclusion is here the electrons are 10 power 16, the holes are 10 power 4 only. So that the comparison is majority is electrons are the majority, holes are the minority carriers, charge carriers. Majority charge carriers in this extrinsic n-type is electrons, minority charge carriers are holes. So current conduction taking place due to both, no doubt, but the majority carrier is due to electrons. Okay, so that is about n-type extrinsic semiconductor, right? Here the procedure is we are adding fifth group element, pentavalent. This is also called pentavalent group elements into the silicon lattice. Okay, similarly, suppose we form a p-type. What is here? Okay, if it is, we can easily construct this similarly p-type semiconductor also. What is here p-type semiconductor? We introduce a boron. Observe here B. B indicates the boron, right? Now observe here the second lines. Indeed, if we can dope silicon with an atom that provides an insufficient number of electrons, then we may obtain many incomplete covalent bonds. Okay, if we dope with insufficient number of electrons, then the resultant lattice become a many number of incomplete covalent bonds. Incomplete covalent bonds means holes, right? For example, in table already we know that boron atom, 3 valence electron, can form only 3 complete covalent bonds in a silicon crystal. So 3 valence electrons are combined with neighboring 3 silicon atoms, so that 3 complete covalent bonds, right? Observe here. 3 valent electrons can form only 3 complete covalent bonds. As a result, the fourth band contains a hole ready to absorb a free electrons. So what is about fourth band here? It is a hole. Incomplete covalent bond, it acts as a hole. Hole also a free charge carrier. Now it is ready to absorb any free electron available, right? In other words, suppose n boron atoms contribute n boron holes to the conduction of current in silicon. So the structure is, okay, this is the structure. Now what happens? Therefore, the example that p-type semiconductor. Why? Because the holes are the majority carriers. Now this boron atom is called the acceptor dopant. The boron atom is called the acceptor. Why? Because it will accept any free electron available in the lattice. Whereas phosphorus is called the donor. Donates the one free electrons. Now, okay, this is some conclusion type here. Let us formulate our results. Okay, for an intrinsic semiconductor is doped with a density Nd donor atoms per cubic centimeter. Then the mobile charge densities are given. Okay, majority carriers is N, minority carriers is P. Then how to calculate minority carriers? Minority carrier density is equal to Ni square by Nd, number of donor atoms. Similarly here, it is a P type. Majority carriers are holes. P here, P indicates the holes. Here small n indicates the electrons. Okay, that is approximately equal to number of acceptor atoms, number of boron atoms. So now here the minority carriers are N. Small n is the minority carriers. Now what is formula? Small n is equal to Ni square by number of acceptors. Okay. Now, what is the typical range? What is typical range? Since typical doping densities fall in the range of 10 power 15 to 10 power 18 atoms per cubic centimeter. So for people use, this is the range. How many number of atoms are added per cubic centimeter to create a p-type semiconductor or to create a n-type semiconductor, right? What is the typical range? 10 power 15 to 10 power 18 atoms per cubic centimeter, right? There is a one small example. It is possible to use other elements as a semiconductor and dopants. Yes, it is possible, right? Some early diodes and transistors were based on germanium rather than silicon. Also, arsenic is another common dopant, right? Okay, not only boron and phosphorus, the people also tried with remaining elements in third group as well as fifth group. Right, this is the summary of so far. Okay, this is intrinsic semiconductor, 4 valency electrons, right? And strong covalent bonds. And coming to the extrinsic semiconductor, silicon crystal. Suppose we add a phosphorus, that is a donor. Here capital A indicates donor. Number of donor atoms per cubic centimeters. So that what happens means available free charge carriers are electrons. So n-type dopant, donor. So what is the majority carriers? Electrons. Similarly, silicon crystal acceptors per cubic centimeter, where the example is boron, right? Now this one is an acceptor. Okay, free majority carrier is acceptor. Okay, that is today class. I think today class almost all covered in intermediate level, right? If you have any intermediate books, please go through, refer intermediate books, right? Today class mainly we concentrated on extrinsic semiconductor material. What is the doping? How to find charge carriers, whether it is electrons or holes in extrinsic semiconductor. Still the mass action law formula still is valid. N into P is equal to Ni square only. Remember this one, whether it is a extrinsic semiconductor or whether it is an intrinsic semiconductor, always mass action law should be satisfied, right? N into P is equal to Ni square only, right? And remember this one, based on this I give a one small problem after completion of this class. Remember this example problem, how to calculate number of electrons or number of holes. Okay, with some doping. Here I change this, instead of room temperature, okay, I can change this value is 600 Kelvin or 1200 Kelvin. Already you have values, right? Suppose I given 10 power 16 phosphorus atoms. Instead of room temperature, suppose 1200 or 900 Kelvin, I can calculate the number of holes, right? Okay, I can give in the problem. And thank you for listening, right? Today class completely, that is mainly already we discussed. You maybe learned at intermediate levels. If you have any textbooks, please refer, right? And thank you for joining, and stay safe. Why? Because number of corona cases increasing in Mandela. So I request all you, please stay safe at home, right? Thank you. Now you may leave the class.